I'm going to be talking about unclonable crypto with unbounded collusions and impossibility of hyperefficient shadow tomography. This is joined for a good Ripple Go. So we all know the very simple principle of quantum mechanics, no cloning principle, which says that any adversary who's given an unknown quantum state cannot create two copies of it. And this very simple principle has found a lot of applications in quantum crypto, starting with quantum money. And a comparatively more recent application of this very simple principle is the so-called copy protection security, which is again a classically impossible security notion that we get in the quantum world thanks to the no cloning principle. So in copy protection, we consider some program software functionality like a, for example, video game or like, for example, Microsoft Excel and so on. And for example, let's say that we're selling this program to people and we don't want them to like distribute this freely and pirate this program. So to prevent this, we encode this program into a quantum state, an unclonable quantum state. And our first requirement is correctness. We want there to be a quantum algorithm that can take this quantum state and take some input to this program and correctly obtains the correct output of the program on this input with high probability. So one implication of this correctness requirement is actually that this quantum state, the quantum encoding of the software, is not actually a single-use state in the following sense. Normally when we measure a state, we destroy it or it's irreversibly changed, but not in this particular case because we have a fixed measurement outcome that occurs with extremely high probability. So by the gentle measurement lemma, we can actually do this in a specific way so that we do obtain the correct outcome, but the quantum state itself is not modified, except maybe in a very small traced instance. So this means that this encoding is almost as good as the original program. We can keep using it on very different inputs, multiple inputs. And the main security requirement we want is codified by the following security experiment called copy protection security. So we consider sampling from some distribution of programs, and then we encode this program into a quantum state, and the adversary receives the state, and it tries to output two entangled quantum registers that are essentially trying to implement this original program, of which the adversary only received a single copy. And the challenger then tests these possible implementations of the original program, and the adversary wins if both implementations or both registers or quantum adversaries pass the verification at the same time. We require that for any secure scheme, the security experiment, in a security experiment, the adversary wins with only very small probability. So this essentially means that any adversary who receives or buys one copy of this program will not be able to distribute it because it cannot output like two working copies. One application of this notion, a specific case, is copy protecting decryption keys of an encryption scheme, like a public key encryption scheme. So in this case, we encode the decryption key into a quantum state, and the adversary receives this quantum state and tries to, again, output two entangled adversaries. And each of these adversaries receive an encryption of a random bit. It's either 0 or 1, and they are trying to guess which case it is simultaneously. And we require that for any efficient adversary, the probability of this happening is at most 1/2 plus negligible. So here the baseline security is actually 1/2, even though there are like two independent challenge bits, because a trivial attack is to just give the original state to one of the adversaries and the other adversary just guesses randomly. So, so far we've been only talking about the adversary receiving a single copy, but this is not a very realistic model because in the real world, for example, again, going back to the case of a video game, for example, maybe thousands or millions of people will be buying these states. And to capture this real world scenario, we define the following security experiment. In this case, the adversary receives any number of copy protected secret keys or copy protected programs, and it tries to output at least one more program that also is functional. So if it receives k initial programs, it tries to output k+1 adversaries that are trying to implement the original program. Again, in the case of encryption, all of these k+1 adversaries will receive challenge encryptions, which are encryptions of either 0 or 1, and they will try to guess at the same time if they get an encryption of 0 or 1. Still, the requirement is that the probability of all of them guessing at the same time is 1/2 plus negligible. Again, the baseline is 1/2 because you can give k keys to the k adversaries, and the last one can guess randomly. So let me also talk a bit about the previous work. So on the impossibility side, it's a folklore result. It's a very trivial result to show that only unlearnable programs or software can be copy protected, even using quantum resources. Because if some program can be learned fully just by evaluating it on various inputs, the quantum state doesn't help you, because just by correctness, you can still learn the full program just by interacting. And in the so-called plain model, where we're not assuming any idealized oracles and so on, even some unlearnable programs cannot be copy protected, as shown by the beautiful work of Anant and Lapleka. On the feasibility side, we have the result of Aronson et al., who showed how to 1-to-2 copy protect. By 1-to-2 copy protect, I mean the very first definition I gave, where the adversary only receives a single copy of the program. They showed how to copy protect all unlearnable programs in the ideal classical oracle model. Again, this is a tight result because in the oracle model, you cannot do copy protection for learnable programs. And going back to real world schemes where we're not assuming any idealized oracles, the beautiful work of Colangelo et al. Have showed how to copy protect in the 1-to-2 setting decryption keys of a public key encryption scheme, assuming the cryptographic assumptions of indistinguishability obfuscation and learning with errors. A follow-up work by Leo et al. Showed how to achieve a construction that is secure in the so-called bounded collusion model, which is like halfway between the initial definition and the actual definition we want to use. So in this case, we assume that there's like a fixed number of programs that we can receive that were fixed at the beginning. And if the adversary receives only that many programs, it cannot win the security game by putting one more program. And they showed how to achieve the security notion for decryption keys of a public key encryption scheme and for some other cryptographic schemes in the plain model, again assuming indistinguishability obfuscation and learning with errors. So as I said, while this definition of 1-to-2 security or bounded collusion security, while they're nice starting points, they don't really capture the security notions that we want for the real world. And in fact, when we go back to this full definition that we want to achieve, where the adversary can receive or buy any number of programs, there's almost a trivial attack for all of the existing constructions. So in both the construction of Colangelo et al. And Leo et al., once different users buy these programs, they can just flip a coin and they just measure the quantum state either in the computational basis or Hadamard basis. And they can just post these measurement results, which are just classical strings, to some online forum. And these measurement results are actually anonymous, so there's also no way of getting caught. And just by using these measurement results, anyone can actually obtain the ability to fully run these programs. So the security, copy protection security is fully broken once these multiple users are collaborating online. So to resolve this issue and to get secure schemes in the realistic model of fully unbounded collusion security model, we obtain the following results. We show how to copy protect in the unbounded collusion resistant setting, the decryption keys of the public key encryption scheme, the signing keys of a signature scheme, and keys of some other cryptographic schemes, assuming indistinguishability obfuscation and learning with errors assumption, which is the same assumption as the previous work. Also, in the classical Oracle model, again, going back to the feasibility results, even in the Oracle model, the result of Aronson et al. Was only for the case of 1-to-2 security in the restricted model. And again, just like the attacks here, there's a very trivial attack for their construction when multiple users are collaborating. So in the Oracle model, we show how to copy protect any unlearnable functionality. Again, in the unbounded fully collusion resistant model, again, this is a tight result because we cannot copy protect learnable functionalities. And finally, we show a connection from our results to the notion of shadow tomography. We show that polynomial time or like efficient shadow tomography is impossible once you either assume some cryptographic assumptions like obfuscation and learning with errors hardness, or unconditionally the information theoretic model of quantum accessible classical oracles. Okay, so before moving on to our results, let me talk a bit about the connection to the shadow tomography. So if you recall state tomography, in state tomography, we are given like multiple samples from some quantum distribution or like multiple copies of a mixed state, and we're trying to learn the density matrix. This is provably impossible to do with only polynomially many copies of this mixed state. And inspired by this, Aronson in 2018 introduced the notion of shadow tomography, which says that we can actually learn a circuit, a classical circuit, such that using the circuit, we can predict many behaviors or like many measurement results of this mixed state with respect to a very large but fixed set of measurements. Using only polynomially many copies, we can actually do this. This is a very interesting notion because, like, again, using only a small number of copies, we can predict like exponentially many different properties of this mixed state or this quantum distribution. But importantly, he was only concerned about the number of copies. But in the real world, we are also bound by time constraints, right? We cannot, for example, run this procedure for 1,000 years. So one question is, can we actually do this procedure, shadow tomography, in polynomial time? Previous works showed that this is impossible to do in some information theoretic model where we're assuming that the procedure has access to some quantum unitary oracle and the states are also associated with this unitary oracle. And coming back to the connection between shadow tomography and copy protection, so our claim is that actually if copy protection in this fully collision resistant setting is possible, then shadow tomography must be impossible. Because if shadow tomography is possible, you can do the following attack to any copy protection scheme. You don't even need to tailor this approach to any specific copy protection scheme. So in the copy protection security game, you just get some number of keys that encode this program that is being copy protected. And you just apply your shadow tomography scheme for the set of measurement result, set of measurements that codify the evaluation algorithm of this copy protection scheme that takes the state and gives you the evaluation result. And by the shadow tomography correctness, we will obtain some classical circuit that allows us to predict all of these like exponentially many measurement results. And this actually means that we are able to just break the copy protection security game and like evaluate this program in a number of times, like any number of adversaries, just by using this classical circuit. So in this work, since we're showing that fully unbounded collision resistant copy protection is possible, assuming these cryptographic assumptions of obfuscation and LWE, we're actually also showing that shadow tomography is not possible to perform in polynomial time, again, assuming these cryptographic hardness assumptions. Or on the flip side of the coin, this actually also shows that if you do have an efficient shadow tomography scheme, this breaks these like widely used cryptographic assumptions using quantum computers. Okay, let me also quickly talk about the types of states that we use in our constructions. So in our construction, we use the so-called coset states where we have an equal superposition of vectors of a subspace state shifted by a fixed vector. Also, we have this phase that depends on the inner product of this vector and the superposition and some other fixed vector S prime. And all of these values, the subspace itself and the random shifts S and S prime, are sampled randomly from this vector space. And also associated with these coset states, we will usually have two programs that allows you to verify membership in this coset defined by the subspace shifted by S, and the dual of it, which is defined by the dual subspace shifted by the other shift S prime. And some nice properties of these states are that we can efficiently generate these states. And once we're given the state by applying QFT, we can actually obtain this dual state, which will pass some kind of superposition verification using this other program P1. Because when you apply QFT, you actually get a shifted superposition over the dual subspace. So one important property that the coset states satisfy that allows us to obtain our copy protection results is the so-called monogamic entanglement property, which we can define using the following crypto-style security game. So let's say that we are sampling the subspace state and the shifts randomly, and we give this coset state along with this verification programs that I define in an obfuscated manner to some adversary, some efficient adversary. And later, this efficient adversary tries to create two entangled quantum adversaries that are trying to output a vector in the computational basis, a measurement result in the computational basis, and a measurement result in the automark basis. And at this point, they even learn the description of the subspace itself, but they don't learn these hidden shifts. And previous works have shown that assuming the security of this obfuscation scheme, no efficient adversary can do this, except with negligibly small probability. So using this approach, the previous work has constructed copy-protected secret keys for a PKE scheme in this restricted model of 1-to-2 security, where your copy-protected key is essentially a tuple of coset states, and your encryption key is just obfuscated programs for checking membership in these cosets. And to encrypt some message, you just sample a random string and you create this obfuscation program that just verifies the authenticity of your coset states, and then it releases the hidden message, which is your encrypted message. And essentially, they were able to show that by this monogamic entanglement security that is satisfied by coset states, this construction satisfies copy protection security in the security model we talked about, which is like 1-to-2 copy protection security. So again, there's a very trivial attack once you get 2 copies here. Once you get 2 copies of the same state, you're actually able to obtain measurement results reliably for both bases, and that kind of breaks the security of the scheme. So to go to the fully collision resistant setting, our solution has 2 steps. So as I said, once you get 2 copies of the same state here, you can trivially break the security. To solve this issue, whenever we're generating a new copy protected key, we actually create an independent coset state. But unfortunately, at the same time, we need to be able to verify these all independent, possibly exponentially many coset states using a very small public key, which allows you to encrypt messages, which again requires checking the authenticity of these coset states. So to achieve this, we actually use so-called pseudo-random coset states instead of using truly random coset states, because using truly random coset states, we're not able to compress all that information into a small public key. And as our main technical contribution, we show that pseudo-random coset states satisfy this very nice collusion-resistant monogamic entanglement game, which again will allow us to obtain collusion-resistant copy protection security. So in this collusion-resistant monogamic entanglement game, instead of receiving a single coset state, the adversary receives any number of independent pseudo-random coset states, and it tries to output 2 entangled adversaries that are trying to answer challenges related to a single instance on one of these coset states. And we are able to show that no efficient adversary can reliably answer these challenges. And using this property, we are able to obtain a copy-protected PKE scheme where, again, your decryption key is a tuple of coset states, but this time it's an independent generated pseudo-random coset state each time. And our public key, in a pseudo-random manner, contains the verification information for all of these possibly exponential many coset states. And encryption follows in a similar manner where to encrypt a message M, you create this obfuscated program that verifies some particular instance of the coset state, and if the verification passes, it outputs your hidden message. And we're able to show that by the monogamic entanglement property in the collusion-resistant setting that we prove, we are able to show that this scheme satisfies collusion-resistant copy protection.
Thank you very much for your talk. Any question? One here?
Wait, so thanks again for your very nice talk, and also I have two questions. So one question is, you say the existence of indistinguishable obstructions and learn with error implies the uh, impossible of efficient shadow tomography. But what about the other direction, like is the existence of the if the not existence of indistinguishable obstruction and the efficient solution of learn with error implies the existence of hyper-efficient shadow tomography. And my second problem is that you say this indistinguishable obstruction is quantum indistinguishable obstruction, or it's just the quantum proof indistinguishable obstruction? Because I assume you could have quantum proof indistinguishable obstruction from learn with errors, but I'm not familiar with the classical cryptography, but I assume you could have learn with error already implies a little bit like I/O. I assume that.
See, so the first question was, does the previous work imply impossibility of efficient shadow tomography? Was that the question?
Yes, the reverse directions of your solution.
Is that the second question, or
No, the first question is the reverse. I mean, because your result is the existence of I/O and LWE implies the impossible of efficient shadow tomography, but it's the not existence of I/O and LW, and the efficient solution of LW implies the existence of efficient shadow tomography.
I would say so. I would say no, at least as far as the current results are concerned. I don't think we know that implication.
Okay. And so the second question is that the I/O here is the quantum proof I/O or quantum I/O?
It's classical I/O that is quantum proof, like quantum secure.
Okay, but okay, I see. Okay, because maybe in further you could like simplify to LWE, because I don't know what classical cryptography is going on, because I assume they have some results like they can construct a quantum proof I/O from LWE, but I'm not familiar with that.
That's like a big question, but it's not solved.
Yes, that's what they are working on.
Yeah.
Yes. Yeah. Thanks again for your talk and your answer.
Thank you. And very quick question.
So the question is, like, my attempt to understand how far we are from practicality. So imagine we have, let's say, very good quantum memory, high fidelity, long time, but it is lossy channel for quantum state transmission, lossy quantum memory. Both quantum money and quantum copy protection, how will it work in these conditions?
That's a good question. So for both of my works, they're like very like fully theoretical. So I'm just assuming that you have a like perfect quantum memory and perfect quantum computer. So I think it would be like a separate question if you can like do these things, at least in a theoretical perspective, if you have like a, as you said, lossy quantum memory. So right now I would say that's not no, like that's an open question. Does that answer your question, or?
Yeah. Thank you.
Okay, thank you very much for the questions, and thank you for the speaker, and thank you again.